This is problem 94 from chapter 13. Determine the normal and frictional driving forces that the partial spiral track exerts on the 200 kilogram motorcycle at the instant when theta is equal to 5/3 pi radians, theta dot is equal to 0.4 radians per second, and theta double dot is equal to 0.8 radians per second squared. Neglect the size of the motorcycle. So we have the angle here, we have r here, we know r is equal to 5 times theta, and so I have the radial direction here, and the transverse direction is perpendicular to that. I want to try and draw this very carefully. So the radial direction is like this, and I know this angle here is 5/3 pi radians, and maybe it would be helpful just to draw the vertical direction first. Okay, so the radial direction is like this, and the transverse direction is perpendicular to that. So like this. So this is the radial direction, and this is the transverse direction. I want to make this a free body diagram. I know that the force of gravity is acting straight downwards. So I have my force of gravity pointing like this. And then I have my normal force, which is perpendicular to the surface of contact. So if you look at the picture here, perpendicular to the surface of contact looks like it's pointed like this. So that would be like this on my diagram here. So the force which is perpendicular to the surface of contact is the normal force. And then we have a frictional force also, and the frictional force is parallel to the surface of contact. So that would be like this. Okay, so now I get to use this equation, which we saw in the introduction, and we haven't used yet. So this is the tangent of psi is equal to r divided by dr d theta. We have r as a function of theta here. This angle psi is the angle between the extended radial line and the tangent line. And along the tangent line, we have the frictional force. So from the extended radial line to the frictional force, which is pointed in the tangential direction, is my angle psi. Okay, so now you can see how this angle is going to be helpful, because if we're going to use Newton's second law for cylindrical coordinates, we'd have to break these forces down into radial and transverse components, and if I'm breaking the forces down into radial and transverse components, I have to know either what this angle is or what that angle there is. So now I can find this angle by saying that is inverse tangent of r over dr d theta. Dr d theta, r is equal to 5 times theta, so dr d theta is just equal to 5, and at the moment we're looking at, theta is equal to 5/3 pi, so r is equal to 5 times 5/3 pi, which is 25/3 pi, and then we can plug that in here, and we have the inverse tangent of r divided by dr d theta, which is 79.19 degrees, which is positive which we should have guessed, because if I go from the extended radial line in the counterclockwise or positive direction, I get to the tangent line here. So remember, if it's positive, you go in the counterclockwise direction, which is usually the positive direction. So that looks good. So now that I know this angle, I can break my frictional force and my normal force down into components. I still have to break the force of gravity down into components, but this should be a little easier because theta, which is equal to 5/3 pi, is in radians, is 300 degrees, and that angle is from the horizontal to the radial line that I have there. So if this is 300 degrees, then I know from here to here is 270 degrees, so this angle here would be 300 minus 270, that would be 30 degrees. So this angle here is 30 degrees. So now I have all the angles that I need. This is 79.19 degrees, so if that is 79.19 degrees, this angle here from here to here is also 79.19 degrees. You can ignore that there. So I need to break the normal force down into radial and transverse components. I need to break the frictional force down into radial and transverse components, and I need to break the force of gravity down into radial and transverse components also. I'm going to try and redraw this again. So this is the transverse direction, and this is the radial direction. And so for the frictional force, this would be the cosine component, and the transverse component would be the sine component. So I think I'm going to be tight on space here. So let's do sine of 79.19 degrees, and this is going to be the cosine component. Then for the normal force, this is the cosine component. And this is the sine component. And then for the force of gravity, this is the cosine component, and the angle for this is 30 degrees. And that's my sine component. That doesn't look so bad. So now I get to use Newton's second law. I have the sum of the forces in the radial direction is equal to the mass times the acceleration in the radial direction. The sum of the forces in the transverse direction is equal to the mass times the acceleration in the transverse direction. I also need to figure out what the radial component of the acceleration and what the transverse component of the acceleration are, and to do that I go back to equation 1232. The radial component of the acceleration is equal to r double dot minus r times theta dot squared, and the transverse component is equal to r times theta double dot plus 2 times r dot times theta dot. I have theta dot, I have theta double dot, I have theta, so I need to find, well, I know r is equal to 5 theta, so I need to find r dot and r double dot. R dot is the derivative of 5 theta with respect to t, which would just be 5 theta dot. R double dot would be 5 theta double dot. And then I want to know what this is when theta is equal to 5/3 pi, when theta dot is equal to 0.4, and when theta double dot is equal to 0.8. So I have 26.18 meters for r, and I have 2 meters per second for r dot, and I have 4 meters per second squared for r double dot. So now I can find my components for acceleration. Theta dot is equal to 0.4. So the radial component of the acceleration is equal to, let me just put it down here, negative 0.1888. The transverse component, I have 26.18 times 0.8 plus 2 times 2 times theta dot, which is 0.4. And that gives me 22.54. Let's just use 3 significant figures to be safe. Okay, so now I have my components for the acceleration. I have my components for the forces. So now I can go ahead and use Newton's second law here. So the sum of the forces in the radial direction, in the positive radial direction, I have the force of friction times cosine of 79.19 degrees plus mg. Do I know what that is? Yes, I do. So that's 200 times 9.81 times cosine of 30 degrees minus n times sine of 79.19 degrees is equal to the mass, which is 200, times the radial component of the acceleration, which is negative 0.1888. So this is one equation and one unknown. Let's call this equation 1. That came from looking in the radial direction. Now I'm going to look in the transverse direction. So I have n times cosine of 79.19 degrees plus the force of friction times sine of 79.19 degrees minus mg, that's 200 times 9.81 times sine of 30 degrees is equal to the mass times the transverse component of the acceleration. Okay, so now we have 2 equations and 2 unknowns. Our 2 unknowns are the normal force and the force of friction, which is what we are looking for. So you could finish solving this on your own, but we will do it together. So we can solve equation 1 for the force of friction. I want to bring these 2 terms over to the other side. And 200 times negative 0.1888 is negative 37.76. I have to bring the 200 times 9.81 times cosine of 30 degrees over to the other side, which makes it negative. So that is negative 1,699. And I have to bring the minus n times sine of 79.19 degrees over to the other side. So that's plus n times sine of 79.19 degrees. And then I have to divide by cosine of 79.19 degrees. And I'm going to let you, no, do we have to simplify it? I guess we just leave it like that for now. And then take a look at, oh, we could do this though. The negative 37.76 minus 1,699 gives me negative 1,737. You could also figure out what sine of 79.19 degrees and cosine of 79.19 degrees are, but I'm just going to leave it like this for now. And now look at equation 2. And I'm going to take what I have here for the frictional force and put that into equation 2. So I have n times cosine of 79.19 degrees plus negative 1,737 plus n times sine of 79.19 degrees divided by cosine of 79.19 degrees times sine of 79.19 degrees, and then 200 times 9.81 times sine of 30 degrees is 981, and 200 times 22.544 is 4,509. The sine and the cosine that I have here, I can make that a tangent of 79.19 degrees, and I have now one equation, one unknown, so I can solve this for n. So I'm going to simplify it a little bit first, so I have n times cosine of 79.19 degrees minus 1,737, so it's this times sine divided by cosine, which is tangent of 79.19 degrees, plus n times sine of 79.19 degrees times tangent of 79.19 degrees, and then the 981 I can bring over to the other side. On the other side it would be positive, and that is 5,489.8. I think this was really like that. Okay, so we have an n in this term here, we have an n in this term here. So we want to bring this term over to the other side and then pull out the n and then divide by what's left. I'm kind of out of space here, so I guess that means you get to do that on your own. So you should get n is equal to 2,735.7. That's in newtons, and you can write that as 2.74 kilonewtons. And then for the frictional force, you can take this value of n and put it back in here, and you should have a frictional force of 5,066, or 5.07 kilonewtons. Okay, so that just comes from solving this for n and then taking that value and putting it back in there.